Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on the binomial theorem. So we're going to use combinations and Pascal's triangle to perform binomial expansions. Now you might be thinking, oh my god, what's this crazy old guy on about? What do combinations have to do with binomial expansions? Aren't we doing probability? Well, this is something that's really cool. It's what I love about maths. Two areas of maths you'd think have nothing to do with each other, well, they absolutely do. So combinations, yes, we were using them in probability, we were using them to count things. They're very helpful in binomial expansion. So I'm talking about when you have to expand brackets of this form. Two things in a bracket to a power. Now you know how to do x plus y squared, that's easy. But by the end of this, you should be able to quickly be able to do something like x plus y to the power of 3, to the power of 4, to the power of 5, so much quicker. In order to do this, we're going to start by going through Pascal's triangle. You may have seen this before. So we start with a 1 at the top, and then there are 2 1s below. Now to get each number, what we do is we start with a new row. Each row starts with and ends with a 1. So what goes in the middle is just the sum of the 2 numbers above it. So 1 plus 1 gives me 2. So the next row, we start and end with a 1. So what goes in the middle? We have 1 plus 2 gives 3, 2 plus 1 gives 3. Next one, we start with a 1. 1 plus 3 is 4, 3 plus 3 is 6, and so on like this. So you're probably thinking, okay, well, this is just simple addition. What does this actually have to do with what we were going through? Well, it turns out there is a very clear link between the entries here and combination. So I'm just going to go down here to row 6. So what we do, just to make everything work, basically, this first row is called row 0, and this is row 1, and so on. And we give each of the entries a number. So the first entry is actually always entry 0. So if I came down to this row here, this would be row 6. So this would be row 6, entry 0 would be the first one. We always start with entry 0. This would be row 6, entry 1, row 6, entry 2, and so on. So one thing that's really cool, the number in row and entry R is exactly what NCR equals. So for example, if I wanted to know what 5C2 is, I would go to row 5, entry 0, 1, 2. This is row 5, entry 2. 5C2, if you put it on your calculator, would be 10. Similarly, if you wanted to know 6C4, if you put that in your calculator, you could get the same number as if you go to row 6, entry 0, 1, 2, 3, 4. 6C4 is this number here that's in row 6, entry 4. It's equal to 15. So Pascal's triangle gives you a quick way to find what NCR is. So how can we possibly use that to perform binomial expansions like this? Well, let's have a look on the next slide. So I've drawn up Pascal's triangle for you here. So let's use this to do quickly the expansion of x plus y to the power of 3. So I know that as a binomial expansion, that's x plus y multiplied by itself 3 times. Now this quickly gets messy. If I want to expand this the way we've been doing, like using FOIL, I have to go x times x times y times x, y times y. I get 4 terms here, and then each of them has to be multiplied by x and then multiplied by y. It takes forever. Here's the quick way we do it. Now, because we're raising to the power of 3, because each term in the expansion will be the result of 3 x's or y's multiplied together, the powers always add to 3. So this is what it's going to be. I start with the highest power of x will be 3, x cubed. So the next term, what I do each time is I decrease the power of x by 1 and increase the power of y by 1. So the next term will be something x squared y. Next term, I'm going to decrease the power of x again and increase the power of y. And then the final term is going to be x to the power of 0. I don't need to write it because it's just 1, times y to the power of 3. So when I expand this, I'm going to have 4 terms that look like this. So what does this possibly have to do with combinations and Pascal's triangle? It turns out that the coefficients of each of these terms can be quickly determined from Pascal's triangle. So because this is a degree 3 expansion, I go to row 3 of Pascal's triangle. These numbers here tell me the coefficients. So it's important that you do them in order. So I'm going to look at these numbers here. 1, 3, 3, 1. They are the coefficients of the expansion. 1, 3, 3, 1. This is exactly what I would have got if I did this ridiculous expansion that took me ages. It's just a quick way to do it. So let's say, for example, we're going to do x plus 3 now to the power of 4. So we're going to follow a very similar process. So the highest power of x is going to be 4. So we're going to start with x to the power of 4. Now the next term, I decrease the power of x by 1. I increase the power of this second thing, this time 3 by 1. So this will be x to the power of 3 times 3 to the power of 1. The next term, decrease the power of x, so it'll be now x squared, and I'm going to increase the power of 3 by 1. So then the next term, I'm going to decrease the power of x by 1, increase the power of 3. And then finally, the last term will be 3 to the power of 4. So that's what the expansion will look like. It'll have 5 terms that look like this. So now I can use Pascal's triangle to find the coefficients of each of these terms. So again, it's important I write them in order. Start with the highest power of x each time, decrease the power of this first thing by 1 and increase this power by 1. And if I do that, the coefficients are really easy. Because this is a degree 4 expansion, I just get them from row 4 of Pascal's triangle. The coefficients will be 1, 4, 6, 4, 1. So just cleaning this up a bit, this time because there are numbers. So the first term's x to the power of 4. So the second one will be 4 times 3, which is 12. So it'll be 12x cubed. The next term will be 6 times 3 squared. 6 times 9 gives me 54. The next term is 4 times 3 cubed. 4 times 27 is 108. And the last term is 3 to the power of 4, which is 81. So this is so much quicker than trying to expand this. Now, I feel like I just need to say this, no offense. Don't try and simplify this any further. They are not like terms. Each of these terms is not a like term, so you can't simplify it any further. And that's how we can use the Pascal's triangle and combinations in binomial expansions. This has absolutely nothing to do with probability, but how cool is it? It's linked to something that was also really useful in probability. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.